There is a quietness to the universe that is difficult for the human mind to truly comprehend. When we look up at the night sky, we are met with a tapestry of light stars, planets, the milky haze of our own galaxy stretched across the dark. To us, the cosmos feels crowded. It feels alive with energy, with burning suns and swirling clouds of gas. But this view, as beautiful as it is a local illusion. It is the view from a crowded room. If you were to leave the Earth, leave the solar system, and travel out beyond the edges of the Milky Way, the lights would begin to dim. If you traveled far enough into the deep, cavernous spaces between the great galactic structures, you would find yourself in a darkness so profound that the concept of sight itself begins to lose its meaning. For a long time, astronomers believed that if we looked back far enough into the deep past, we would find a similar darkness. They believed that there was a time, long before the familiar spiral arms of galaxies existed, when the universe was simply empty. Not empty of matter, but empty of light. A time of silence. A time of waiting. This era is known to science as the Cosmic Dark Ages. It is a period that existed hundreds of millions of years after the Big Bang, a long, stretching epoch where the universe was filled with nothing but drifting hydrogen and helium gas. No stars had yet ignited. No galaxies had yet spun into motion. There were no quasars, no supernovae, no points of brilliance to break the monotony of the endless night. According to our best theories, according to the mathematics that describe the evolution of the cosmos, this darkness should have lasted for a very long time. The universe, in its infancy, was a cold, neutral sea. It was a fog. And in that fog, gravity was working, but it was working slowly. It takes time to build a star. It takes time to pull together enough gas, atom by atom, grain by grain, until the pressure becomes great enough to spark the nuclear fires that create light. So, when we built our greatest machine, the James Webb Space Telescope, we prepared ourselves to peer into that darkness. We wanted to see the very end of those dark ages. We wanted to catch the first tentative flickers of the first stars turning on, one by one, like distant candles in a vast, windless cathedral. We expected to see a slow awakening. We expected to find a universe that was just barely beginning to stir. We expected to look deep into the abyss of time and see mostly shadow, with perhaps a few rare, faint smudges of red light marking the birth of the cosmic dawn. But the universe, it seems, does not like to do what we expect. When the James Webb Space Telescope opened its golden eye and stared into the deepest, darkest patches of the sky places where the Hubble Space Telescope had seen absolutely nothing, it did not find the empty void we predicted. It did not find a silent, sleeping infant universe. It found light. It found bright, massive, fully formed structures standing defiantly in the dark. It found galaxies that were too big, too bright, and too mature to exist. It found light where there should have been nothing. This discovery has sent a gentle ripple through the world of astronomy, a whisper of confusion and awe that is still spreading. It challenges the story we have told ourselves about how the universe began. It suggests that in the dark, while we thought the cosmos was sleeping, something was happening, something rapid, something powerful, something we do not yet understand. To understand the magnitude of this mystery, we must first understand the darkness itself. We must transport our minds back to the beginning, before the light we know today existed. Imagine the universe shortly after the Big Bang. The initial heat has faded, the violent expansion has cooled, the cosmos is now a vast, expanding cloud of hydrogen. It is dark, not because there is nothing there, but because the matter that exists is cold and neutral. It absorbs light. It is a fog that shrouds everything. For hundreds of millions of years, this fog drifted. There was no sound, for there was no atmosphere to carry it. There was no light, for there were no stars to cast it. There was only gravity, the patient sculptor, working in the dark. Gravity is the weakest of the forces, but it is relentless. It never stops. Across the vast distances, it began to pull the gas together. Tiny fluctuations in density places where there was just a slightly bit more gas than the surroundings began to grow. The gas fell inward, clumping together, growing denser and hotter. Our models told us that this process is slow. In the early universe, the gas was moving, streaming, resisting the pull. It should have taken eons for the first clouds to collapse enough to ignite. And when they did ignite, those first stars, the population 3 stars, should have been solitary giants, burning hot and blue and dying quickly. They should have been rare. The first galaxies should have been messy, small, irregular things. Little clumps of stars huddling together for warmth in the cold. They should have been dim, barely visible even to the most powerful lenses we could construct. This was the timeline we had constructed. It was a timeline of gradualism, a timeline of slow, steady growth, from the simple to the complex, from the small to the large, from the dark to the light. Then came the launch. On a Christmas morning, the James Webb Space Telescope lifted off the Earth, folding itself into the fairing of a rocket, a traveler destined for a lonely outpost a million miles away. It was an act of hope. We were sending a machine of mirrors and sun shields to a place called L2, a stable point in gravity's shadow, where it could keep its back to the sun and look outward into the eternal night. The telescope cooled down. It let the heat of the Earth and the sun radiate away until its mirrors were colder than the surface of Pluto. This cold was necessary. The light from the early universe has traveled for over 13 billion years to reach us. In that time, the expansion of the universe has stretched that light. What began as visible or ultraviolet light from young stars has been pulled and stretched into the infrared spectrum. It is no longer light that our eyes can see. It is heat. It is a faint, ancient warmth. To see it, Webb had to be cold. It had to be still. When the first images arrived, the world marveled at the clarity. We saw nebulae in our own galaxy looking like mountain ranges of dust. We saw the planets of our solar system with new rings and moons, but the cosmologists were waiting for the deep fields. They pointed the telescope at a patch of sky that looks empty to the naked eye, a patch of sky smaller than a grain of sand held at arm's length. They opened the shutter and let the ancient photons, the travelers that had been journeying since before the Earth was born, strike the gold-coated beryllium mirrors. They expected to see the faint red dots of the first baby galaxies. Instead, the image was filled with light. There were thousands of galaxies, but not just the small, ragged clumps we expected. There were spirals, there were disks, there were structures that looked shockingly modern, and most disturbingly, there were galaxies that were incredibly bright. To be that bright, a galaxy needs stars. Lots of stars, billions of stars. Or it needs a supermassive black hole that is feeding voraciously, turning matter into light. But these galaxies were seen at a time when the universe was only 300 million, 400 million years old. In cosmic terms, this is mere moments after the Big Bang. It is like walking into a nursery, expecting to find newborn infants, and finding instead fully grown adults, speaking in complete sentences, standing tall. It doesn't make sense. There wasn't enough time for them to grow. There wasn't enough time for gravity to pull that much gas together. There wasn't enough time for the light to become that bright. And yet, there they were. James Webb found light where there should be nothing but the faint haze of beginnings. It found maturity in the era of infancy. It found a bustling metropolis in a time that should have been a lonely frontier. This is the central mystery we face today. The darkness was not as dark as we thought. The silence was not as silent. The universe woke up earlier, faster, and more violently than we ever imagined. As we drift through this narrative, we will explore what this light means. We will look at these impossible galaxies. We will ask how they could have formed so quickly. Did the laws of physics work differently back then? Did gravity behave in strange ways? Or is there something fundamentally wrong with our clock, with the way we measure the age of the universe itself? Let us float now, away from the Earth, past the orbit of the moon, past the glittering mirrors of the telescope, and cast our minds back into that deep, red-shifted past. Let us try to visualize the moment the lights turned on. Imagine the darkness again, the hydrogen fog. But now, imagine that hidden within that fog, there are seeds. Seeds of dark matter, invisible scaffolds that are pulling the gas in much faster than we thought possible. Perhaps the universe was never truly silent. Perhaps the darkness was teeming with activity, hidden from us only by distance and time. The light that Webb captured is a ghost. It is a messenger from a time that no longer exists. The galaxies we see in those images are not there anymore. They have evolved, merged, aged, and perhaps faded away billions of years ago. We are looking at a memory, but it is a memory that contradicts our history books. It is a feeling akin to finding an ancient artifact in a layer of rock where no civilization should have existed. It forces us to rewrite the story of our origins. And so, we stand on the precipice of a new understanding, the nothing. We expected was an illusion of our own making, born of limited sight and limited imagination. The universe is far more fertile, far more creative, and far more luminous than we gave it credit for. The light is there. It has always been there, streaming through the void, waiting for us to build a net fine enough to catch it. Now that we have caught it, we must decipher its message. The arrival of data from deep space is a quiet event. There is no thunderclap, no sudden flash of lightning across the sky. There is only the silent stream of binary code traveling through the vacuum on radio waves, caught by the great dishes of the deep space network on Earth. Numbers flowing into servers, pixels filling up screens in quiet, climate-controlled rooms. But within that silence, a revolution occurred. When the astronomers first processed the deep field images from the James Webb Space Telescope, there was a hesitation, a collective pause. The data they were looking at seemed wrong. They were analyzing the redshift of these distant points of light. Redshift is the astronomer's measure of distance and time. As light travels through the expanding universe, the space it travels through stretches. This stretching pulls the waves of light apart, making them longer. Blue light stretches into red. Red light stretches into infrared. The farther the light has traveled, the more it has been stretched, and the higher its redshift number. A redshift of 10 or 11 corresponds to a time when the universe was less than 500 million years old. Before Webb, seeing anything at redshift 10 was a heroic feat, pushing the Hubble Space Telescope to its absolute breaking point. We had found only a tiny handful of candidates, and they were faint, uncertain smudges. The first data dumps from Webb showed galaxies at redshift 11, then 12, then 13, and even hints of redshift 14 and beyond. But it wasn't just the distance that was shocking, it was the intensity. These objects were luminous. They were shining with the brilliance of billions of suns. In the standard model of cosmology, the framework we use to understand the history of the universe, this shouldn't happen. At such an early time, matter should still be diffuse. The halos of dark matter, which act as the gravitational cradles for galaxies, should be small. They shouldn't have had enough time to gather enough gas to birth so many stars so quickly. It is a problem of efficiency. To make a galaxy that bright, that early, you would need to convert almost 100% of the available gas into stars instantly. You would need a process of star formation that is perfectly efficient, wasting nothing, pausing for nothing. But in the local universe, the universe we see around us today, star formation is messy and inefficient. It is slow. Gas clouds collapse, stars form, but those new stars blast out radiation and winds that push the remaining gas away. They choke off their own food supply. It is a self-regulating process. A galaxy usually turns only a small percentage of its gas into stars. So, how did these ancient galaxies do it? How did they burn so bright, so fast? Let us look closer at one of these anomalies. Consider the object known as JADE, JWST, a name that sounds like a license plate, but represents a portal to the dawn of time. This galaxy exists at a time only 290 million years after the Big Bang. It is currently the distance record holder. When we look at it, we see it as it was then. If the universe were a 100-year-old human, we are looking at a picture taken when that human was a toddler of 2 years old. We expected a toddler. We expected something small, unformed, perhaps crawling. Instead, JWST is surprisingly large. It spans over 1,600 light-years across, and it is bright. Its light implies that it already contains hundreds of millions of solar masses worth of stars. But there is something else. The light from this galaxy is not just the light of a feeding black hole. Often, when we see a bright dot in the deep universe, it is a quasar, an active supermassive black hole swallowing gas. That light is harsh, concentrated in a single point. But the light from JADE's JWST is spread out. It comes from the galaxy itself. It is the light of stars. This means that in less than 300 million years, this patch of space managed to pull itself together, overcome the expansion of the universe, cool down its gas, and ignite hundreds of millions of stars in a synchronized burst of creation. It is the first flicker on a scale we did not think possible. Imagine standing in that early galaxy. The sky would not be black, it would be ablaze. The stars would be packed closer together than they are in our neighborhood. And these would not be the gentle yellow suns we know, they would be monsters. The first stars, the population 3 stars, were made of pure hydrogen and helium. Without heavier elements like carbon or oxygen to cool them down, they had to be massive to collapse. Some were perhaps hundreds of times the mass of our sun. They burned blue-white, radiating with a ferocity that strips electrons from atoms. They lived fast, perhaps only a few million years, before detonating in supernovae of unimaginable power. The light we are seeing from these Webb discoveries might be the collective glow of these giants. But there is a catch. The light we see also carries the fingerprints of heavier elements. We see signs of oxygen, we see signs of carbon. These elements, oxygen, carbon, nitrogen, are not born in the Big Bang. They are cooked in the hearts of stars. They are the ash of nuclear fusion. To have oxygen in a galaxy, you need a generation of stars to have already lived, died and exploded, scattering their ashes into the cosmos to be incorporated into the next generation. Finding significant amounts of oxygen and dust in a galaxy only 300 million years after the Big Bang is like finding a written novel in a room where the alphabet has just been invented. It implies that the cycle of life and death, the cycle of stellar evolution, was spinning incredibly fast. Everything was accelerated. The clock was ticking at a frantic pace. This brings us back to the title of our journey, finding light where there should be nothing. The nothing was our assumption that the universe needed a long rest after the Big Bang. We assumed it needed hundreds of millions of years of dark ages to cool down and get organized. But the light tells us that the universe hit the ground running. One possibility is that our understanding of gravity is slightly off. Perhaps in the early universe, density fluctuations grew faster than our equations predict. Maybe the dark matter halos, the invisible skeletons of galaxies, formed earlier and were clumpier than we thought. Another possibility is that star formation works differently in the pristine conditions of the early cosmos. Maybe without heavy elements, gas clouds don't fragment into small stars like our Sun. Maybe they collapse cleanly into massive clusters, converting gas to light with a terrifying efficiency. Or perhaps there is something even more exotic at play. Some cosmologists have whispered about dark stars, stars powered not by nuclear fusion, but by the annihilation of dark matter particles. These hypothetical stars would be cool, giant, and incredibly bright, capable of mimicking the look of an early galaxy. Whatever the answer, the first flicker was not a tentative spark, it was a bonfire. It suggests that the universe has an innate drive toward complexity. It does not want to remain a soup of particles, it wants to structure itself, it wants to light up. As we stare at these images, these little red smudges on a black background, we must remember what they are. They are the ancestors. They are the forges where the very first heavy atoms were created. The carbon in your cells, the oxygen in your lungs, the iron in your blood. The story of those atoms begins here, in these impossible galaxies that lit up the dark too soon. We are looking at our own chemical heritage. We are looking at the moment the universe stopped being a simple cloud and started becoming a machine for creating life. The darkness was deep, yes, but the light was eager. And as Webb continues to stare, pushing deeper, looking for even fainter, redder points of light, we are beginning to realize that the Dark Ages might be a misnomer. There may have been no Dark Ages at all, only a brief pause before the fireworks began. The curtain did not rise slowly. It was ripped open. If we could fly through the universe as it was 13 billion years ago, our eyes would struggle to make sense of the geometry. We are accustomed to the majestic shapes of the modern cosmos. We are used to the grand design spirals, galaxies like the Milky Way or Andromeda that look like spinning pinwheels of light, perfectly symmetrical, with graceful arms trailing through the vacuum. Shutterstock. Explore these shapes tell a story of time. They tell a story of billions of years of rotation, of settling down, of gravity smoothing out the rough edges until a galaxy becomes a flat, orderly disk. Because of this, astronomers expected the early universe to look like a construction site. They expected it to be messy. They predicted that the first galaxies would be train wrecks, clumpy, irregular blobs of gas colliding with one another, violent and shapeless. In the standard theory, a beautiful spiral galaxy is the result of many small, ugly blobs smashing together over eons, eventually calming down into a spiral. Therefore, the further back you look, the messier it should get. But once again, the James Webb Space Telescope opened its eye, looked into the deep past, and found something that should not be there. It found elegance, it found structure. Alongside the bright, inexplicable light we discussed, Webb revealed the shapes of these ancient islands. And they were not the shapeless blobs we predicted. Many of them were distinct, organized disks. Deep in the data, in the light that left its source when the universe was a mere toddler, we found rotating galaxies. We found disks that had already settled down. They were calm, they were ordered. Finding a rotating disk galaxy just a few 100 million years after the Big Bang is like finding a fully built skyscraper in a city that supposedly broke ground yesterday. It implies that the chaotic phase of the early universe, the phase of violent collisions and turbulence, settled down much faster than our computer simulations said it could. The gas cooled, collapsed, and spun up into a disk with a speed that defies our understanding of cosmic friction. But there was another shape, perhaps even more surprising, that Webb began to reveal in great numbers. Astronomers began to notice that the early universe was filled with cosmic bananas. When they analyzed the 3D structure of these distant galaxies, they realized that many of them were not round and they were not flat disks like plates. They were long. They were shaped like cigars or cucumbers or surfboards. In the language of geometry, we call this shape prolate. In the modern universe, prolate galaxies are rare. Most galaxies are oblate, like pancakes, or spherical, like basketballs. But in the deep past, it seems the universe preferred the shape of the surfboard. Why? The answer may lie in the invisible skeleton of the universe, the cosmic web. We believe that the universe is threaded with vast filaments of dark matter. These filaments stretch across the void like the strands of a giant spiderweb. Hydrogen gas flows along these filaments like water flowing down a river. It seems that in those early days, the galaxies were growing by surfing these filaments. They were sliding along the dark matter strands, eating the gas as they moved. Because they were forming inside these narrow rivers of material, the galaxies themselves became narrow and long. They were shaped by the flow of the river they were born in. This paints a mesmerizing picture of the early cosmos. It was not just a random scattering of explosions, it was a network, a glowing, thrumming web of connections. Imagine billions of long, glowing cigars of light sliding along invisible highways, channeling gas into their hearts to feed the birth of new stars. It suggests that the nothingness was actually a highly organized highway system. The darkness was structured, and within these strange shapes, something else was lurking, something heavy. To create the amount of light Webb is seeing, we discussed the need for many stars. But there is another way to make light, a black hole. We know that supermassive black holes sit at the centers of most modern galaxies. Our own Milky Way orbits around Sagittarius AHA, a gentle giant 4 million times the mass of the Sun. We used to think that these monsters grew slowly, feeding on gas and other stars over billions of years. But Webb has found black holes in the early universe that are far too big for their age. We have found black holes that are millions, even billions of times the mass of the Sun, existing when the universe was less than 1 billion years old. This presents a profound chicken and egg problem. Did the galaxy form first and then a black hole grow in the center? Or did the black hole form first and the galaxy grow around it? The data from Webb is hinting at a terrifying possibility. The seeds were heavy. In the standard story, a black hole starts when a single massive star dies. It leaves behind a black hole maybe 10 or 20 times the mass of the Sun. That is a small seed. To get from 10 solar masses to 1 billion solar masses takes a long time. You have to feed it constantly. But black holes are messy eaters. As they eat, they blast out radiation that pushes the food away. There is a speed limit to how fast they can grow. The black holes Webb is seeing are so big that they break this speed limit. They couldn't have started from a single star. This leads to the theory of direct collapse. Imagine a cloud of gas in the early universe, so pure and so massive that it doesn't break apart into stars, it doesn't fragment. Instead, the whole thing, a cloud weighing as much as 100,000 suns, collapses under its own weight. It bypasses the star stage entirely. It crunches down directly into a massive black hole, a heavy seed. If this is true, then the early universe was punctuated by these silent, catastrophic events. Giant clouds vanishing in an instant, punching a hole in the fabric of space-time, creating a massive anchor that would instantly begin pulling in everything around it. This would explain the light. These young, massive black holes would be feeding voraciously. The gas falling into them would heat up and shine with the brilliance of 1 trillion stars beaconing across the dark. So, when we look at those little red dots in the Webb deep fields, we are likely looking at a mix of things. Some are galaxies filled with distinct, incredibly efficient stars. Others are gas clouds swirling around a heavy seed, a newborn monster screaming into the void. Both of these realities, the surfboard galaxies and the heavy black holes, tell us the same thing. The early universe was a place of extreme physics. It was a place where matter organized itself with a ferocity and speed that we do not see today. The nothing was not empty. It was pregnant with potential. It was a coiled spring waiting to snap. As we gaze at these images, we are forced to let go of our prejudice that early means primitive. In the cosmos, early might mean powerful, it might mean pure. The structures we see are not rough drafts. They are masterpieces of a different era, built by forces that have since quieted down. The universe we live in today is the old age of the cosmos, slow, settled, conservative. The universe Webb sees is the wild youth, but this wildness comes with a cost. The more we find these mature, massive, structured things in the deep past, the more strain we put on the very foundation of cosmology. We are pushing the timeline to its breaking point. If you find a child who looks like an adult, you have to ask, is this really a child? Or is there something wrong with the calendar? This question leads us into the deepest tension in modern science. Time is the invisible river that carries the universe forward. In our current understanding of science, we believe we know how long the river has been flowing. We have measured the current, we have mapped the banks. We state, with a fair degree of confidence, that the universe began 13.8 billion years ago. This number, 13.8 billion, is the bedrock of modern cosmology. It is derived from the Standard Model, also known as lambda CDM. It is calculated by measuring the expansion rate of the universe, the Hubble constant, and running the film backward to the moment of the Big Bang. It is also confirmed by measuring the oldest light in the sky, the cosmic microwave background, which is the afterglow of the Big Bang itself. For decades, this timeline has held firm. It fits the data, it explains the distribution of galaxies, it explains the abundance of hydrogen and helium. It is a good map. But the James Webb Space Telescope is drawing jagged lines all over this map. The problem, simply put, is that 13.8 billion years might not be enough time. When we look at a galaxy at a redshift of 14, seeing it as it was just 300 million years after the beginning, and we see that it is massive, rich in metals, and structured, we encounter a compression problem. We are squeezing too much history into too little time. Imagine you are an archaeologist. You dig into a layer of soil that you know for a fact is 5,000 years old. You expect to find stone tools, perhaps some simple pottery, but instead you find a complex mechanical watch. You have two choices. Choice A, the ancient people were somehow able to build mechanical watches using technology we don't understand. Choice B, the soil layer is not 5,000 years old, it is much, much older. In cosmology, we are currently wrestling with choice A. We are trying to find ways to make stars and galaxies grow faster. We are tweaking our models of supernova feedback, of magnetic fields, of accretion rates. We are saying the universe is 13.8 billion years old, but the early universe was just incredibly efficient at building things. This is the most likely answer. We call it astrophysical uncertainty. It means the physics of gas and stars is complex, and we just underestimated how fast nature can work when the universe is dense and crowded. But there is a whisper in the back of the room, a whisper that favors choice B. What if the timeline is wrong? What if the universe is older than 13.8 billion years? There are exotic theories that have lingered on the fringes of science for years, which are now getting a second look. Some theorists propose that the universe did not begin with a singular Big Bang, but is part of a cycle, a bounce. If the universe existed before the bang, if it was contracting before it expanded, then perhaps some seeds of structure survived the bounce. Perhaps the black holes or the dark matter clumps were already there, carried over from a previous eon. If that were true, the galaxies wouldn't have to start from scratch, they would have had a head start. Another possibility, slightly less radical but still groundbreaking, involves the nature of the expansion itself. We use the redshift of light to measure distance and time. We assume we know exactly how the universe has expanded over the eons. But what if the expansion hasn't been constant? What if the universe expanded differently in its youth? If our ruler is broken, then our measurements of time are wrong. A galaxy that looks like it exists at 300 million years might actually exist at 600 million years. That extra time would solve the problem. It would give the stars time to cook, the galaxies time to spin. But changing the ruler breaks other things. It messes up our understanding of the cosmic microwave background. It creates conflicts with other measurements. So, the scientific community is in a state of creative tension. The mainstream view is still that the standard model is correct, but incomplete. We are missing a piece of the physics of star formation. We are underestimating the fog. Consider the role of dust. In the early universe, we expected very little dust. Dust comes from dying stars. No dying stars, no dust. But Webb sees a lot of dust. Dust is tricky. It absorbs blue light and re-emits it as infrared heat. It can make a young galaxy look older and redder than it really is. It can mimic the signature of a massive galaxy. Perhaps some of these impossible galaxies are actually smaller, younger galaxies that are just incredibly dusty. They are masquerading as giants. But even accounting for dust, the problem remains. The sheer number of bright objects is the issue. The nothing that we expected to find was based on a universe that moves at a specific speed. The universe Webb found is moving at a sprint. This crisis is actually a gift. In science, we learn the most when our predictions fail. If Webb had looked out and seen exactly what we expected, faint, blobby, rare galaxies, we would have patted ourselves on the back, closed the textbooks and said, "We solved it." We would have stopped looking. But because Webb found light where there should be nothing, we are forced to open the books again. We are forced to question our assumptions about gravity, about dark matter, about the life cycles of stars. We are forced to be humble. The light from the edge of time is telling us that the universe is more capable than we imagined. It suggests that life and the conditions for life might have arisen much earlier than we dared to dream. If galaxies formed quickly and planets formed quickly, then chemistry and biology could have started eons before the Earth was even a glint in the solar nebula. The Dark Ages might have been a time of hidden life. Far beyond the orbit of the Moon, drifting in the silent shadow of the Earth, the James Webb Space Telescope continues its vigil. It is a lonely machine. Its sunshield, the size of a tennis court, blocks the blinding glare of our local star, allowing its golden mirrors to remain in a deep cryogenic freeze. It is the coldest object for millions of miles. It waits, it stares. It gathers the faint, stretched ghosts of photons that have traveled for eternity. We built this machine because we were afraid of the dark. We were afraid that if we looked back to the beginning, we would find a void that lasted too long. We feared that the universe was a cold, empty room that took eons to warm up. But the telescope has given us a gift. It has shown us that the universe is not empty, it is not slow, and it is not silent. The light we found where there should be nothing is more than just a data point. It is a revelation about the character of the cosmos we live in. It tells us that the universe has a bias toward creation. It seems that matter does not want to stay apart. It wants to come together. It wants to condense. It wants to ignite. The gravity that pulls dust into stars and stars into galaxies is not a lazy force. It is urgent. It seized the very first moments of existence to build the cathedrals of light that we now inhabit. Think of what this means for us. We are creatures made of heavy elements. We are made of carbon, oxygen, nitrogen, iron. These are things that did not exist in the Big Bang. They had to be forged. They had to be cooked in the nuclear hearts of stars and scattered by the violent deaths of supernovae. If the Standard Model had been entirely correct, if the Dark Ages had truly been a long, slumbering era of silence, then the arrival of these elements would have been delayed. The chemistry of life would have been pushed back by hundreds of millions of years. But because the universe woke up early, because the first flicker was a bonfire, the ingredients for life were scattered into the void much sooner than we thought. The oxygen in the water you drink, the iron in your blood, the calcium in your bones, these atoms have a lineage. And thanks to Webb, we now know that this lineage stretches back closer to the beginning of time than we ever dared to hope. We are not latecomers to a slow-developing story. We are the inheritors of a rush to exist. The nothing was an illusion. When we looked at those dark patches of sky with our old eyes, with our smaller telescopes, we saw a void because we could not see the heat. We could not see the infrared glow of the cosmic dawn. We were like someone standing in a dark forest, unable to see the animals moving in the shadows because we didn't have night vision. Now we can see, and the forest is alive. It is populated by surfboard galaxies sliding along dark matter rivers. It is anchored by heavy black holes that grew up too fast. It is illuminated by stars that burn with a ferocity we can scarcely imagine. There is a profound comfort in this. It suggests that the universe is fertile. It suggests that the conditions for complexity, for beauty, and perhaps for life are woven into the deepest fabric of space-time. The darkness is not an absence of things, it is merely a canvas waiting for the paint. As we conclude this journey, let your mind drift back from the edge of the universe. Pull back from the red-shifted fires of the first galaxies. Float past the great clusters of the cosmic web. Drift through the spiral arms of ancient galaxies that have long since merged and changed. Come forward in time, past the birth of the sun, past the cooling of the earth. Return to the present moment. The light from those first stars is raining down on Earth right now. It is landing on the roof of your house. It is landing on the trees outside. It is landing on your skin. It is too faint to see, stretched by its long journey into invisible heat, but it is there. We are constantly bathed in the light of the beginning. James Webb found this light by looking at a patch of nothingness. It reminded us that nothing is often just a placeholder for something we do not yet understand. The mystery of how these galaxies grew so fast remains. The crisis of time, the tension in our equations, the confusion of the astronomers. This is not a failure. It is the thrill of discovery. It is the universe inviting us to learn more. We thought we knew the story. We thought the book was written. But the universe has turned the page back to the first chapter and showed us that we missed the most exciting part. The lights turned on early. The show began before we took our seats. And what a magnificent show it is. In the vast, silent, expanding dark, there is light. There has always been light. And as long as we have the courage to build mirrors and point them at the void, we will never truly be in the dark. The universe is a place of light, and so are we.